Welcome to my class. Today we will be discussing the logic gate as building block. How logic gates can be constructed into a small circuit and the smaller circuits connected together to form another bigger module. We will discuss this concept by taking the example of how to implement the parallel adder using full adders. To complete this solution, we first need to know what is a parallel adder. A parallel adder is a circuit that will add two binary numbers in parallel. Let us take the example of 4-bit binary numbers. 4-bit parallel adder. This will be a circuit which will perform an addition between a 4-bit number A and another 4-bit number B. If we take an example of A, let it be a number 1101 and B another 4-bit number, say 10111, and the circuit which will perform this addition is called as a parallel adder. If we represent these 4 bits of A as this bit being A0, A1, A2, A3, 4 bits of A. Similarly, this being B0, B1, B2 and B3, the 4 bits of the number B. We know this parallel addition, and any practical addition will always have to consider the carry in coming from any previous column. So there is another carry in over here. For the time being, we assume it is 0. So the first addition is 0 plus 1 plus 1. We know that this gives the result 1 and a carry of 1. So 1 plus 1, a 0, a carry of 1. Here you have 1 plus 1 plus 1. This gives a sum of 1 and a carry of 1. And the last 1 plus 1 gives you a 0 here and a final carry of 1. So by adding two numbers, both of which are 4-bit, the result which is obtained is also, this is your 4-bit sum. So you got a 4-bit sum, this one, and this is the final carry out. If you label the sum bits as S0, S1, S2, S3, so the 4-bit sum is S0, S1, S2, S3. The number A was A0, A1, A2, A3. The number B was B0, B1, B2, B3. This is the process of addition of two 4-bit numbers in parallel. The circuit that performs this function is called as the parallel adder. Having understood the working of the parallel adder, let us go on to understanding how the parallel adder will be implemented. So as we always see that the first step in understanding any combinational logic circuit is to draw its block diagram. So if we understand or draw a 4-bit parallel adder, we know that it is a circuit which will add two numbers A and B, but keep in mind that A is also a 4-bit number. This is a number A represented by A0, A1, A2 and A3. Similarly, the second number is B, which is again a 4-bit number. So the number B is B0, B1, B2 and B3. Both these are 4-bit binary numbers. And the circuit which performs the addition of these two bits, these two numbers A plus B, is the parallel adder. And we have just seen that the result generated by a parallel adder will be the sum, which we have just seen is a 4-bit sum labeled by S0, S1, S2, S3 and generated a final carry of the circuit labeled as carry out, C out. And let us not forget that there is a carry in coming from any previous addition circuit. So this is the block diagram of the parallel adder. To implement this parallel adder, we have to keep in mind that this parallel adder is performing nothing but the addition between A0 and B0. The carry generated by this addition is going as the carry in for the next column, which is adding A1 and B1. The carry generated from this addition goes to the next column, which adds A3 plus B3. The carry generated from the third column goes to the fourth column, which adds A3 and B3, giving the sum S3 and the final carry of the circuit called as carry out. So if we understand this properly, we see that this addition, this first addition, will be performed by a full adder. We may call it as full adder 0. The second addition will be performed by another full adder. We may call that as full adder 1. The third column being added by another full adder 2. And the last one, another full adder we need to do the addition for the last column. So we have 4 full adders. We need 4 full adders. Full adder 0 to add A0 and B0. Full adder 1 to add A1 and B1. Full adder 2 to add A2 and B2. And full adder 3 to add the bit A3 and B3. And each time, keep in mind that when A1 and B1 is added, the carry generated from here goes as C in, carry in to the next column. The carry from A2 plus B2, the carry out, goes as carry in for the next column, which adds A3 and B3. If this understanding is clear to us, we may now proceed to draw the final circuit of the parallel adder. We will have to still draw it in the form of a detailed block diagram of the 4-bit parallel adder, and we saw that this 4-bit parallel adder needs 4 full adders. We label those adders as full adder 0, full adder 1, the full adder 2, and the full adder 3. Recall that the full adder 0 to add bits A0 and the bit B0. What does the full adder 1 add? It adds A1 and B1. The full adder 2 adds the bits A2 and B2. The full adder 3 adds A3 and B3. And each time the carry out of the full adder 1 goes to carry in of the full adder 1. The carry out from here goes as carry into this. The carry out of this goes as carry into this. And the last generates the final carry out. The initial carry in is added to the first full adder. So if this is one full adder 0, this is another full adder, this is another full adder, and this is another full adder. We can now translate this into blocks by drawing this as a full adder 0, which will add the bits A0 plus B0. Then you have another full adder 1, another one, full adder 2, and followed by another full adder 3. Full adder 1 will add A1 plus B1. Full adder 2 will add A2 plus B2. Full adder 3 will add A3 plus B3. So if we mark the inputs like this, A0, B0. The inputs to this are A1 and B1. This will have the input A2, B2. The last full adder will have A3 and B3. The first full adder will also add the column, the bit Cin, which will be coming from a previous column. And the full adder 1 will generate the sum bit S0. Full adder 1 will give the sum bit S1. This will F sum bit 2. And the last full adder will give the sum bit 3. And the carry generated from the last full adder will be the final carry out. And this together will form the 4-bit sum. Now you are left with the carries. So we saw the function that the carry out of the first full adder, FA0, will go in as carry in to the next full adder. The carry out from here will go as carry in to the next full adder. This carry goes as carry in to the next full adder, and this gives the final carry out. This completes the block diagram of the 4-bit parallel adder. So we label this circuit as a 4-bit parallel adder. If you are asked how many inputs does the 4-bit parallel adder have and how many outputs does the circuit have, so this you can see from the circuit. We also had seen in the previous block diagram that how many inputs are there? 4 for A, 4 for B, 1 for the carry in. So it has 9 inputs. The outputs generated are 4 bits for the sum, 1 for the carry. So it has 5 outputs. 4 plus 1, 5. So the parallel adder is a circuit having 9 inputs and 5 outputs. This circuit is available in the form of an integrated circuit, IC 7483. The IC 7483 is 9, 10, 14. It is a 16-pin IC. Now, why do you need 16 pins for this IC? 9 pins for the input plus 5 for the output, 9, 10, 14, and 1 pin is required for the supply voltage, which is labeled as VCC, and another 1 pin for the ground pin. So 9 plus 5 plus 2, 16 pins. So this is a standard IC 7483, which is a parallel 4-bit parallel adder IC circuit. Coming back to the detailed block diagram, let us complete our discussion by analyzing that the parallel adder is built from how many number of gates. Recall that the full adder is a circuit which was built from how many gates did the full adder have? This had 5 gates. This had another 5 gates. This was another 5 gates. And this is another 5 gates. So a total of 5 into 4. The parallel adder is a circuit constructed from 20 gates. And what are those 20 gates? Remember, recall that a full adder had, one full adder had 2 XORs, 2 ANDs, and 1 OR gate. So keeping that in mind, let us finally say that a parallel adder 4-bit has 2 into 5, 2 into 4, 8 XORs, 2 into 4, 8 ANDs, and 1 each, 4 OR gates. So this totals to 20 logic gates. The 4-bit parallel adder is a circuit, combinational circuit, having 8 XORs, 8 ANDs, 4 ORs, implemented by a combination of these 20 logic gates. And as an exercise, you may just draw the full adder as a logic circuit of these 5 gates and the complete circuit of a full adder using 20 gates. To summarize our discussion of the parallel adder, we started with the understanding of 4-bit parallel number addition, a 4-bit number A and another 4-bit number B added in parallel giving the 4-bit sum and the final carry output, and also including an initial carry in from the previous column. Having known the process of addition, we went on to see the block diagram. The block diagram of the 4-bit parallel ladder. It is a circuit which adds two numbers A plus B, both the numbers being 4-bit numbers. So 4-bit number A, A0, A1, A2, A3, 4-bit number B. So this is your 4-bit number B. This is the 4-bit number A. When these are added together, it gives you the 4-bit sum and the final carry out. And any addition would always have an input carry bit carry in coming from the previous addition column. I also told you that this is a standard circuit available in the form of an integrated circuit numbered IC 7483, which is a 16-pin IC. 16-pin because 4 for the sum, 4 for the two numbers, 4 to 3, 12. This is a 13, this is 14, and it will have a ground pin and another for the supply pin, so it becomes a 16-pin IC. Standard, available commercially in the market. Then we went on to see the construction of the 4-bit parallel ladder. The detailed block diagram. We understood that the parallel ladder 4-bit needs 4 full ladders. If we label those as FA0, FA1, FA2, FA3, this is what the 4 full ladders did. FA0 adds A0, B0, and FA3 adds A3, B3. Output of carry out of the first goes as carry into the next. Carry out of the next goes as carry into the next full ladder. With this understanding, we finally drew the detailed block diagram of the 4-bit parallel ladder, and we saw that it was built or implemented by using 20 logic gates. These are the 4 full ladders. These are the 2 bits each. This is the final 4-bit sum. This is the final C out. This is the carry in, and the detailed block diagram leads us to the understanding that the parallel adder, 4-bit parallel adder, is implemented by using 8 XOR gates, 8 AND gates, 4 OR gates. All these gates are 2-input logic gates. So a total number of 20 logic gates are required to implement one 4-bit parallel adder. Thank you.